In this lecture, we'll discuss graphs. And graph is one of the most important data structure. In fact, this is the second last data structure that we are discussing in this course. So, what a graph really is, let's just start discussion, and you'll see how this graph is considered as one of the most important data structures so far. So, first of all, consider this collection of vertices. What we call a vertex, let's just focus on that point first, that what are we representing here. This vertex can be a city, and these are multiple cities of a country maybe, or maybe these vertices, they represent different countries. Similarly, these vertices can represent different people, different persons. Maybe these vertices represent different subjects that you are studying in your undergraduate degree. So the collection of these entities is what we call the set of vertices, and we represent them using this notation. And then the size, that is the number of these vertices, we represent it with this bar sign, that is the magnitude of V, or the size of V of this set is equal to n. So whenever we want to see how many entities are there in the graph, then we say the size of the set of vertices, and we represent that value as n. So after these vertices, what we have is that we can join or connect or associate vertices with each other. So that's very simple concept. As we said, these vertices can be two persons. So maybe this V1 is a person and V2 is related to that person. Maybe that's a blood relation. Maybe that's a friendship relation. Maybe these two people, they are the class fellows. They maybe they are moving on. They are traveling to the same destination. They have traveled to the same destination. So this relationship is something that we want to actually, uh, in fact, that's the important information that we want to capture in our data structure. So this edge, it's actually the essence that you have when you design an application of a graph. Okay, so whenever you design an application and you choose that you have multiple entities that are connected with each other, and the relationship is something that you need to represent, and you want to have certain degrees of those relationships as well. So that makes it a complicated data structure instead of having just a simple tree or a linked list. So that's where this graph data structure comes in handy. Okay, so we can represent any relationship between two vertices here using this edge, and this E represents the set of edges. So this is this starting basis of the set of edges, and then we have these tuples as an element in the set. So this tuple that further has two elements shows or represents that V1 and V2 are actually associated with each other, and we should have an edge when we draw this graph on a paper. Okay, so V1, V2 are connected, V3, V5 are connected. So you see there is an edge here. Then V4 and V8 are connected, and so on. We have these tuples for every edge in the graph. Okay, and when two vertices have an edge between them, we call them that these edges are adjacent to each other. So here, uh, generally speaking, Vj is adjacent to Vk when there is an edge between Vj and Vk. And as you can see here, is that this edge is bidirectional. It is if V1 is connected to V2, then V2 is also connected to V1, which means that having an edge between V1 and V2 means that V1 is adjacent to V2. Similarly, V2 is also adjacent to V1. Okay, so that's how we define a graph, that we have a set of vertices and then we have a set of edges. So if we combine these two sets, we can denote a graph completely. So now we'll see some applications of graphs. So as I said earlier, a graph can be used to represent this driving map. So, for example, we have these some vertices here: v1, v2, v3, v4. Now I'll show all these application using these four vertices. So if I'm representing a driving map here, these v1, v2 are the maybe intersections or cities in a geographical location. And then if I connect v1 and v4, then there is a road that connects v1 and v4. Okay, so this is how we can represent our driving map. Then for alien traffics, these vertices could be the destinations all over the world. And if there is a direct flight from V1 to V4, then we can connect V1 and V4. Okay, so that's how we represent alien traffic. For computer networks, these vertices can be some nodes. And for example, if V1 and V4 can communicate with each other, then we have an edge between these two vertices. More specifically, I would like to say here that V1 and V4, if they are physically connected via a wire, then we actually draw an edge between V1 and V4. Okay. Otherwise, if I have an edge between V1 and V2 as well, then in a computer network, V4 can send a message or communicate with V2 using V1 as well. So V4 is connected to V2, but it's not a direct connection. Whereas we are saying that direct connection can be a physical line between V1 and V4. Similarly, if we go to some recent applications of graphs, uh, what you can see here is a mesh of different vertices, and then there are different edges between those vertices. Now, this is actually an output of a visualization that we run here, in which we actually try to capture this web document graph. Okay, so we have these web pages as a vertex, and then what we have is that if a web page links to another web page, like you have a URL of another page on this page, then what we have is that we connect these two vertices. So for example, if there is a vertex between this tiny node and this tiny node, if we have an edge between these two vertices, these two web pages, it means that somehow this web page, this first web page, maybe it has a link that points or that refers the reader to this next vertex. So on the other hand, um, we can have social networks like Facebook, Twitter, Instagram. So on those networks, the information is very crucial. We have different entities, and this connection may represent anything that happens between these two entities. It can be friendship, maybe. It can be that a person um, has gone to the same college as the other. Maybe these two people buy same things. Maybe these two people live in the same vicinity. Maybe these two people are related by blood to each other. Okay, so this relationship in a social network can represent anything, and in fact, this can be a mixture of all these things. Okay, we'll see in coming slides that these different types of relationships, they can also be modeled in a graph using some complicated definition of an edge. Okay, so one important thing here to note is that the application of graphs are unlimited. There can be many applications, and we can have very big uh, graphs as well. Like here we have a social network that is 1.3 billion users. This figure is taken from the um Facebook users of 2016. So that's quite old figure, but still it has grown many times here. This number of users can be represented using a graph. So whenever you implement a graph, you need to make sure that you have the best possible or the most efficient application, because this graph might be used to store a tremendous amount of data. Okay, so that's one takeaway from this slide, where I've shown you the applications that model a situation where we have the data size that is enormous, and we need to model that in a graph. So you definitely have some constraints on storing such a big graph, and then actually running an algorithm on top of that graph, which can actually show you some results or calculate some results in a reasonable amount of time. So these social networks, they are there, and they help uh, s- take some output from the connections of these users. So of course these also raise some concerns, that a graph that is well modeled, it can actually uncover many hidden relationships as well, where we can say that having a very naive data structure would not have helped. So having a well-defined graph structure, it can actually give us some insights to predict the future interactions of different entities in the graph network. It can also predict how a user will behave in a certain situation. So there can be many applications if we model a graph in a way that can give us results in a reasonable amount of time, in a reasonable usage of space. So there are limits. And we have to take care of those limits of resources as well. Okay, so after that, now we'll see, after these applications, we'll see some definitions and some terminologies that are used widely in the graph theory. So let's go through these terminologies one by one. So first of all, we have this term of undirected graphs. So what we have already seen is that we have a set of vertices to show a graph, and then we have a set of edges. Here the size of vertices is 7 and the size of set of edges is 9. So given these sets, if we draw this graph, it would be something like this. I have these A, B, C, D, E, F, and G graphs, vertices here from the vertices set, and then there are different connections. There are different edges between these vertices. So A and B are connected. So we have this edge here between A and B. A and D are connected, and so on. But what we have here is that if there is no direction of this edge, which means that if A is connected to vertex B, then B is also connected to vertex A. It can be a relationship, maybe, if I just say these two are the family members. If A is the family member of B, then B is also a family member of A. It can be that if A has gone to school A, then and B has also gone to that school, then these two persons, person A and person B, are schoolmates. So if A is a schoolmate of B, then B is also a schoolmate of A. If A is a class fellow of B, then B is also a class fellow of A. So that's an undirected graph where we have only one entry for this connectedness between A and B. Okay. We have the other definition definitely is the directed graph. We'll see that in a moment. But first, we see some more detailed definitions, terms that are related to undirected graphs. So first of all, um, uh, formally speaking, what we denote for a undirected graph is that this tuple that we stored in the set of edges, it is unordered, which means if I write it as Vj, Vi, it represents the same thing. Okay, so that's an unordered pair. Okay, that's the formal definition of the undirected graph, that all the edges are unordered pairs. Okay, okay, then for graph that has maybe this number of edges, that is the size of the set of edges, then what we have is that maximum number of edges can be that, of course, we can have one edge between any two vertices. So we want to couple these vertices together. So all the vertices given in pair can be total number of these v square vertices, given this formula that VC2. Okay, that's VC2. That's combination formula. So when we say that this is the total number of combinations for these vertices, so that's how we actually open this formula, and the formal answer and the final answer is that we have, if we just talk about the uh, asymptotic behavior, that is order of v square. So in an undirected graph, we can have at most v square number of edges. Okay, so that's what you need to remember. That would come in handy in some coming slides. Then we can implement this undirected graph in two ways: adjacency matrices and adjacency lists. We'll see them as well in this lecture. But first, we'll talk about some more terminologies. So degree of a vertex is that how many edges are there or incident there on a vertex. So for this vertex A, if I say, if I want to know the degree of this vertex, I would just count these number of edges. So these are 3 edges that are incident on this vertex A. So the degree of vertex A is 3. For vertex B, this is 1, 2, 3, and 4. For maybe vertex G, this is 0. For vertex F, this is 1. Okay, so this is how we what we call when we this is the definition of the degree. So this is how we actually calculate the degree. We just count the number of edges that are incident on a vertex. So in this graph, degree of A, degree of D, and degree of C are 3. Similarly, degree of B and E are 4. Degree of F is 1, and degree of G is 0. Okay. We'll formulate some algorithms based on this definition of the degree. And then the next definition is that we have in a graph, we can actually pick a part of this graph and call it a subgraph of this original graph. Okay, it can pick some vertices, maybe removing 1 or 2 vertices, maybe removing 1 or 2 edges from the original graph. We take another graph that is a subgraph of this original graph. Okay, and of course, to complete the definition, every graph is a subgraph of itself as well. Okay, so after removing any number of edges or any number of vertices from the original graph, we can come up with another graph that is the subgraph of the original graph. Okay, so this definition would also be used in some algorithms in some later lecture. Then we have this definition of a path. Okay, so starting from this node A, if I want to go to node F, I would have to traverse these edges and reach this node F. Okay, for a path in an undirected graph, it means that we just want to note down these edges that we have taken to reach this node F. That's a path. Okay, so if I start from A, I could have gone to directly to E, then C and F. So there can be many paths that can lead me from A to F. Okay, but whenever I want to list down a path, or I want to write down a path, I would write the exact sequence of the edges that I've taken to reach my destination. So here, if the formal definition is that if a path is written as V0, v1, v2 up till vk. So I've started from a vertex and I've reached a vertex k, that's the destination vertex. Okay, it means that I have taken these edges v of, for example, here J starts from 1 to k. So V of 0 and V of 1, that's one edge that I've taken. That's the first edge that I've taken from the source to the other, to the node 1, V1. Then from V1 I move to V2, then from V2 I move to another node, then eventually from the second last node I move to VK. So I need to note down the exact sequence of edges that I've taken from source to destination, and that's called, if I write down those vertices in a sequence, it makes it it's the path from source node to the destination node. In this specific graph, this highlighted, this red path can be represented as A, B, E, C, and F. Okay, and if I want to tell the length, then I would count these number of these edges. So there are 4 edges, so the length of this path is 4. Similarly, in this graph, the length of this specific path that starts from A to B, then B to E, E to C, C to again B. Now this B is repeated in this path, and from B to D. Okay, so this A is the source node. This is another definition, and this D is the destination. Okay, so from source node, I've taken certain edges, and upon those actions, I have repeatedly visited this vertex B. Okay, so this is a behavior that we would like to keep in mind, because some algorithms focus on keeping this repetition to a minimum, or just try to avoid this repetition of vertices in a path. Okay, so that's another example of a path. So if I just want to list down the vertices that were A, B, E, C, B, D. So B is repeated here. Okay. Then we can have a trivial path where source and destination are the same, that is the node A. So this is a trivial path of length 0. Now from this path definition, we can define another definition, that is a simple path. So in this simple path, there are no repetition. That's the key point here. So in the previous example where B was repeated, that was not a simple path. Some algorithms work only on simple path. They try to find the simple path between source and the destination vertex. So that's why you should also know that in a simple path, we actually make sure that there are no repetition of vertices. Okay, and then there is this loose end here, that except for the first and the last vertex. So this we can repeat this first node multiple times and the last node multiple times, and this definition comes in handy where we talk about this cycle. So a simple cycle is actually a vertex where we start from the same vertex and we end on the same vertex. That is, the source and the destination are the same. Okay, in that way we would repeat the first and the last vertex, and that's a cycle. And for a simple cycle, we do not repeat any vertex on the way. We start from the source vertex, we move to different vertices, and then come back to the same vertex. So that's a cycle. But if we do not repeat any vertex on this path, then that's a simple cycle. A very common example of this behavior would be that a person starting from his home may go to a shopping mall first, then may go to some other place, and eventually come back to his home, his or her home. So, which means that when we actually try to map this type of behavior on a graph, then we would like to figure out the number of simple cycles, or maybe we are interested in the simple cycles that this person has taken. Okay, so there are application of simple cycles as well. Then the next definition is of connectedness, that we already discussed. Now we discussed about the connectedness of two vertices. Okay, so two vertices are connected when there is an edge between those vi and vj vertex. But if all the vertices, okay, um, or let me rephrase this statement, two vertices, they are said to be connected. The first definition that we saw was that there was a direct connection between two vertices. But then there's another definition that, for example, this is vertex A, this is vertex B, and then we have a vertex C, and B is connected to C as well. This definition of connectedness says that this node A is connected to node C because there exists a path from node A to node C. Okay, so this path exists between node A and node C, which means that node A and C are connected. Okay, that's the definition of the connectedness of two vertices. Whereas a graph is connected when we can actually run this connectedness definition on every node. That is, every node is connected to every other node via a path. So definitely, which means that in this specific graph that I've just drawn, if I just remove this arrow from this graph, so this specific graph, here, if I talk about this node A is connected to B directly, and this node is connected to C via a path. Whereas this node B is directly connected to A and C. C is connected to B directly, whereas C is connected to A via a path. So all the nodes are connected to all other nodes, which means this graph is connected. Okay, this definition is actually very important. Um, Sometimes you would like to see, for example, in a computer network, if a vertex or a node is accessible or not. And if you want to check that, you would like to check the connectedness of the entire network. Similarly, if you just want to see if an airline, uh, it has destination to all the countries in the world or not, it means that you would actually like to check the connectedness of the graph that you have made, that you have actually maintained for this specific airline operations. Okay, so the connectedness actually shows you the extent of the information that can flow from one end to the other end. Okay, I hope this makes sense. Okay, so a little more in detail. This is an example where all the vertices are connected to each other via a path, and then, for example, if I just remove all the ink, here in this second graph, what we have is that this red triangle, this is part of the graph, but it's not connected to other nodes. This specific node is not connected to any node in the blue part of the graph. And similarly for these two other nodes in the red graph as well. So these three vertices are the disconnected portion of the entire graph. Okay. An application of this could be that, for example, if I share an information with one person, can this information reach to a person a few steps away from my connectedness? Maybe if a hoax or a fake news can be, or if a hoax or a fake news would reach to some person or not. Maybe if I just distribute an information to a given set of people, would this information be disseminated to the entire society or not? Maybe if we talk about the university or a campus of a university, if I just announce something that maybe there's a quiz in the next class, and if I tell this information to just the CR, the representative of your class, would he be able to reach out everyone in the class or not? So if he's connected to everyone, maybe via WhatsApp, maybe via uh, some um some other social network, then he would be able to reach them. Otherwise, there is no connection between some people with the CR. So then those people would not be reachable. So that's the definition of connectedness. That's the actual application of the connectedness, definition of the connectedness. Okay. So after all these definitions between vertices and the edges, now we'll move on to something slightly different, that is the weight inside a graph. Okay, so as I said earlier, that these edges can represent anything between these two vertices. Okay, so here we can also, on these edges, we can represent a number or some information. I would actually disagree with just storing a number on this edge. We can store any information that we want to process while we process these two vertices, and we can use this information in that specific algorithm. So here, for example, like a distance, we can say that A and B are two cities that are 3.5 miles away from each other. Then we can say that A and B are maybe two specific points, and this is the energy consumption that we start from A and reach B. This is the fuel that we consume to reach from source A to destination B. Then we can say maybe this is the overall cost, maybe not just the fuel cost, it's also the cost of maybe the wear and tear of the vehicle as well. Maybe we have to take a lunch while on the way. So this 3.5 may represent anything. Maybe what we can do is that we can have a breakdown 3.5 kilometers, and maybe for these 3.5 kilometers or 3.5 miles, I have used maybe zero point 0.3 liters of petrol, and then the cost, maybe the cost of the lunch was maybe a few dollars, maybe or a few rupees, etc. So we can represent all these three information, these three values. We can store them in one. Maybe if we talk about C++, we can say that we can store all this information in one structure or a class, and we store that specific object in this edge. Okay, so we'll see the exact implementation, how we implement this edge, but the information that it represents, is called the weight of the edge. Okay, so a graph that has weights on the edges is called a weighted graph. So the difference between a normal graph, weightless graph with the weighted graph is that when we measure the distance between two vertices, we actually add up this weight of the edges, and we actually show the exact sum of the edges taken to reach from source to destination. So on this specific edge from A to G, we have taken two edges. So on this simple path, the cost is 5.1 plus not this point, this 3.7. So the cost is 8.8. Okay, so the cost from to reach G from A is 5.1 plus 3.7, that is 8.8. Okay, and similarly in the same graph, there's another path from A to G, that is this A to C, C to F, and F to G, and the cost of this path would be 1.2 plus 1.4 plus 4.5, that is 7.1. Now you see this 7.1 is smaller than the previous cost, that was 8.8. And similarly, what we can have is shortest path as well on this weighted graph, that is from, in fact it looks little longer, but the cost that we have actually incurred is smaller, taking the smallest possible edges on the way to the node G. So this is actually an application of the shortest path that we can get using our graph. Okay, so a graph can give us shortest paths as well. So there are many applications of shortest paths as well. Maybe we can discuss them in a later lecture, but there are many applications of finding the shortest path when we represent our model using a graph. Okay, so after finding these shortest path, the next definition is that a tree is also related to graphs, is that a tree actually adds some conditions on the graph data structure, and we actually a restrictive mode of a graph is a tree, and the restrictions are that a graph should be connected if it's a tree, and there should only be a unique path between any two vertices. Okay, there should not be multiple paths like we saw in the previous this example, that we have multiple paths from A to G. Okay, but if we have only one path from each node to every node to every other node, and that path is just one unique path, then this graph is called a tree. So in these three graphs, we do not see any but you can say we only have simple paths here. Starting from this node, if I want to reach this specific node, I can only take this one unique path to reach this destination. I cannot take any other path to reach this specific destination. So it means that uh, a graph is actually, if it's a set of it actually caters for a set of applications, then the applications that a tree can cater for is a subset of those applications. Okay, in fact a tree is a subset or a subgraph of a graph. Okay. um, Um, so if we have these definitions, what difference would we have is that the consequences are that the number of edges should be exactly v minus 1, because if I add just one edge, then there should be a repetition. For example, in this tree, if I add just one edge, maybe between these two vertices, it creates a duplicacy. Okay, maybe if I do not add this edge, any if I connect any two vertices here using an extra edge, it would be a redundant edge here. Okay, so removing all the redundancy from a graph makes it a tree. And for that, in order to connect, for example, two vertices, we only need one edge. In order to connect three vertices, we need two edges. In order to connect maybe four vertices, we need three edges. If I add one more edge, it would actually be redundant. The nodes were already connected via three edges. Adding a fourth edge is redundant. It would not add anything to the connectedness of the already created tree. So it should be exactly v minus 1. And if the edges are less than v minus 1, then the connectedness is not there. Okay, that's the condition that we can check if we just want to check the connectedness of a graph. There should be at least v minus 1 edges. And apart from that, we would check the uniqueness of the edges as well, that they do not create a loop in the graph. Okay, so that's one relationship that we have seen in a tree. Then the graph is acyclic, which means that it does not have a cycle. That's the definition that I was talking about. So we can actually check if a graph is a tree by using these two uh, conditions, and then that's what I've discussed, that adding one more edge must create a cycle. Okay, so then the next definition after the trees is the forest. Okay, so if I remove multiple edges from a connected graph, and if I keep doing that, at first it would maybe disconnect the graph and make it divide it into two partitions. Then upon removing some more edges, it can actually uh, further divide the partitions into sub partitions, and at a later stage it can create multiple trees from that one graph. So here in this specific graph, I have removed some edges, and what I've come up with is four different trees. So having four different trees means that I have a forest that is multiple trees. So there can be situations where the data set that I have, it contains a forest. So if I prove that it's a forest, then I can actually deduce some other meaningful information from that specific part, specific graph. But definitely finding the forest or proving that a given data set is a forest uh, is uh, is really helpful sometimes. Okay? So when we have a forest, the consequences are that the number of edges should be less than vertices. So that's what when I said that if I have less than v minus 1 edges, then definitely there are connectivity or connected there is disconnectedness in the graph. So when we have disconnectedness in the graph, then we have multiple trees in the graph. Okay, and then the number of trees is v minus e. Okay, so that's I guess you can clearly see. And if I remove any more edges, I would create more trees. So if I remove this edge, I would divide or partition this one tree into two trees. I would divide it into two. So removing any edge from a tree divides it into two trees. So similarly in the forest, if I remove an edge, definitely it would add more trees in the forest. Okay. So that's a forest, and now that's all for the terminologies of the undirected graphs. So now let's move on to the next form of the graphs, that are the directed graphs. Definitely, the undirected graphs are a superset, whereas this directed graph, what they add here is that they simply say that uh, if V1 is connected to V2, then we should also mention the direction of the connection. It's not necessary. It does not necessarily mean that V2 is also connected to V1. So that's the direction of the relationship. Okay. So there are several applications where the relationship between two entities is directed. For example, what we can say here is that, for example, this V1, maybe this is the supervisor and this V2 is an employee. So V1 is the supervisor of V2, but V2 is not the supervisor of V1. Okay. So to represent such relationships, we can add the direction to the vertex as well, to the edge as well. So in this specific scenario, what we do is that this pair is now this tuple v1 v2 is now ordered. I cannot replace this v1 v2 tuple with v2 v1. This v2 v1 actually captures the information that there is another edge that goes from V2 to V1. Okay, so this order now matters. Okay, so writing these edges in the correct order is important here. So in this specific V3 and V5 example, you can see that V5 V3 and V3 V5, there are two different entries for these two edges. So directed graphs, they are actually more restrictive than the undirected graphs, but of course they are required in some applications. We do not want to lose this specific information that only V1 is connected to V2, whereas we cannot connect V2 with V1. Okay, so then adding just the direction adds both terminologies here. Now the degree is redefined for the connected for the directed graphs. So there is now this term out degree and the degree and the in degree term. So out degree means for this V1 is that V1 has two outgoing edges, so the out degree is 2, whereas there is no incoming edge, so the in degree of V1 is 0. Similarly, maybe for V5, this out degree is 1, 2, and 3. It has three outgoing edges, so out degree of V5 is 3, whereas in degree is 1 and 2. So in degree of V5 is 2. Okay, so for the directed graphs, we would actually like to uh, differentiate between the in degree and the out degree as well. Then similarly, the definition of path. Now this path can only be in the direction of the edges. Okay, we cannot go in the opposite direction of the edge. So V naught, V1, V up till Vk, if this is a path, then we definitely have a directed edge between V0 and V1, V1 and V2, and so on. Okay, the direction of the edge also matters here. And of course, the path length of the path is the same definition that we discussed in the undirected graph. And then the simple cycle, of course, is the same definition that we now we would only add the direction as well, and we would come up with the definition of the directed of the same path or simple path or simple cycle definition with the direction. Then the connectedness, the definition of connectedness is slightly different here. A graph is strongly connected if there exists a directed path between any two vertices, which means that if I follow the direction of the edges and still the graph is connected, that is, every vertex is connected to every other vertex, then the graph is said to be strongly connected. On the other hand, there can be cases when if I just drop the direction of the edges, if I just drop the direction of the edges and the graph becomes connected, it means if I just say that this direction doesn't matter, V1 is connected to V2, and if I just consider this graph as an undirected graph, and that undirected graph, that underlying graph that is undirected, if that's connected, it means that the graph is weakly connected. It can be the application of this weakly connected definition can be, for example, if I have a road between two cities, then I have another city connected with the second city, for example, but for some reason this road was one way and this road was also one way. So this city A was connected to city C, but this city C is not connected to city A. For example, for some reason, I want and maybe uh, for some specific situation, I just drop this direction that now these roads are not uh, one directional. The traffic can flow in the both ways. For example, during the peak school or the office hours, when the schools are over and the students have to come back to their homes, usually the roads in front of the schools, they are made one way, and when that rush passes away, then the actually the those roads, they are rush free and we can use them in both the directions. So definitely there is a road there, but for some specific scenarios it becomes directed, and for some other scenarios we can take it as undirected as well. So a directed graph in some application may be treated for as an undirected graph as well, and that if that undirected graph gives us some solution, we can use that solution to answer a question as well. Okay, so this connectedness of a graph can be removed for some specific scenarios and then re-edit just to restore the original shape of the graph, but that's specifically for an application. Okay, so again, the definition of subgraph, I think I should skip that because that's the same definition, adding the direction of the edges. Then the weighted directed graph, of course, it's a directed graph where we have some weights on the edges as well. Okay, so after all these definitions, now the important part here is that we see that how we implement these graphs. So a graph can be represented using two of these ways, either as an adjacency matrix or as an adjacency list. Okay, a graph can be directed, undirected, weighted or unweighted graph, but we can represent using these two methods. So let's see them one by one. For an adjacency matrix, what we do is that we create a matrix where we have, that's the n cross n matrix if we have n vertices. So if we have these six vertices, we create an 6 cross 6 matrix. And for the edges, what we do is that we store a one or true value on the index where we have an edge. So there is an edge between vertex 0 and vertex 1. So we store a true here. And this is an undirected graph, which means there should be an edge between 1 and 0 as well. So we place a symmetric edge on this part as well. So this is the edge. This t is for the edge between 1 and 0, and this t is for 0 and 1. Similarly, if I have a false here, I would also have a symmetric false on this point as well. If I do not have an edge between 0 and 2, then I also do not have an edge between 2 and 0. So this specific, if you see, uh, matrix, this is symmetric matrix. So if I divide this diagonally, I have this repetition of the matrix, the upper portion, and in the upper portion as well as in the uh, bottom left portion. Okay, so an adjacency matrix for an undirected graph is symmetric, where I have this value true, or I can store a boolean value 1 on the indices where I want to represent an edge, and I store a 0 or the value false where I do not have an edge. So there is no edge between 0 and 2, and then there is no edge between 0 and 4. So 0 and 4 do not have an edge, 0 and 2 do not have an edge, so I store a false here. Okay, so that's how we store graph in an adjacency matrix. Of course, this is the very simple representation, but let's talk about some more details of this adjacency matrix. So the first detail here is that we can also store the weighted graph in this matrix. So for the weighted, for the weighted graph, what we do is that we would simply, instead of storing 0 or 1, we would store the weight of the specific edge on the place on the specific index in the matrix. So that it makes the matrix the as the weighted graph matrix. Okay, so we can store weighted graphs in the matrix as well. Okay, then the last thing that we would like to show here is that we can store a directed weighted graph as well. So in this case, I do not have an edge between 0 and 1. In fact, I have an edge between 1 and 0 with the weight 0.3. So between 1 and 0, I have this weight 0.3, but for 0 and 1, I do not have a weight. So in that case, I would store a value 0 in this specific case. Okay. So this adjacency matrix can store any type of a graph, whether it is it is an undirected graph, it's a directed graph, or a weighted, if I add weights or not. So this is how we use this adjacency matrix. Now let's analyze this adjacency matrix. So the first thing here is that representing this specific unweighted directed graph in this matrix, I have only, maybe if these are 1, 2, 3, 4, 5, 6, 7, 8, these are 11 total number of edges. So I have placed only 11 ones here, and it requires the memory of 9 cross 9, that is 81 cells, and I have used only 11 of those cells. Okay, so that's the actual issue here in using the adjacency matrices, that the matrix can be very sparse. Okay, then if I want to determine if if a vertex j is adjacent to vertex k, I would simply go to the index v of j and v of k. So that's if j is 1 and k is 2, so I would say 1 to this, I would check this specific cell. So it's order 1. I can simply jump to that specific location in a matrix. So that's order 1. Then if I want to find all the neighbors of this vertex, for example, vertex 1, then I would need to check all this complete row and see how many ones are there. So if there are 3 ones, the sum would be 3. So I would just need to add up the values in this row, and I would come up with the number of neighbors if the graph is unweighted. Otherwise, I would just check the cells where that are non-zero in this row. So the size of the row is the number of vertices, so that's the order of v. Okay, and then it's sparsely populated. Like I said, there are only 11 ones in the matrix of 81 cells. So that's the wastage of the space. In fact, I only needed to store this information that there are only 11 edges. I should have stored only 11 values and not the other 70 zeros in this matrix. Okay, so if you have a situation or an application where you do not have much connectedness, then you would not go for the adjacency matrix. Okay, instead, what you would do is that you would go for an adjacency list. So now in this adjacency list, what we have is that we have this one array of vertices. Maybe this can be a linked list as well, but this can be an array of vertices. And on every vertex, what I have is a linked list of edges on every vertex. So if vertex 1 has only 2 edges, that is, it has an edge from 1 to 2 and then another edge from 1 to 4. So this one has only these 2 edges. So I have only stored 2 elements in this linked list. In this way, I have only stored the values that are required to be stored, and I have not stored those zeros that were stored previously in the adjacency matrix. Okay, I have only stored the exact specific edges, the information of the edges in the linked list, and I have not stored anything where there is no edge. So it's saving a lot of space for us. So let's see if this what's the analysis of this adjacency list. So what the memory requires is this array, and then the size of these nodes. So the overall memory would be order of vertices, that's the array, then the number of edges. So I only store the information about the exact number of edges. So the overall memory requirement is order of v plus e. Okay, only storing this array and then these linked lists, the complete linked lists, all these linked lists have the e number of entries in there. So For the weighted graphs, what I do is that I store two values for one edge, that is the vertex and the weight. So this vertex 1, it has an edge towards vertex 0 with a weight of zero point 0.3. So both these values are stored inside the information of the edge. So here we have this array, and then these are the linked lists, and that's why it's called the adjacency list. Okay, so we have spaced a lot of space here where the data was sparse. Okay, so in case, for example, in case if we just have these names as the strings, for example, this if this a person, it can be the maybe the ID number, or maybe the name of that person, or maybe some unique string. If that's the string, then we can simply hash this value, this 0 or 1. Maybe the name was person XYZ. We performed the hash function. We applied that hash function on this string, and what we got is the value 0. That is why we stored this vertex on index 0. Then similarly for some other string, we would get index 1 and then index 2 and so on. So we can hash these values, string values, onto this array of vertices, and then on every vertex we can have the list of the edges that this vertex has. Okay, so that's the idea. Just moving on to some C++ code of this implementation is that we can have this class of single node, which has this the ID or the number of the adjacent vertex, then the weight, and the next vertex. So this becomes the list of edges. Okay, so there's the single node. And what I do is that I simply create an array of this single node. So if I have this array of 16 elements, what essentially I have is that I have stored, uh, I have enough space for 16 vertices to store their list of edges, because this vertex would have a link to another. If I just create an edge here, I would create another memory that is similar to this memory, and it would also have a next edge. So that becomes a linked list, and I can grow this linked list as much as I can. So that's the simple implementation of an adjacency list. I hope this makes real sense. So that's it about the implementation of the graphs. Now we'll talk about some applications of the graphs. So the first application that is these are some classical applications. The application is of Euler's tour, and in this tour, this is the Königsberg in Russia, where there is actually there are around 7 bridges on a river. And what essentially we want to do is that we want to devise a walk through the city that would cross each of the 7 bridges only once. So if I am in this part of the city, I can come to this interior part of the city using either of these 2 bridges. But if I reach here, then I can move to this outer part, lower part of the city using either of these 2 bridges, and then I can go back from this edge from using this bridge. Then I move to this bridge, and similarly from this bridge, so on. But the way I have done this simulation, it essentially does not find this tour. So this tour means that we need to devise a walk. We need to find a walk in this graph, in a graph, in any given graph, where we can traverse all the edges without repeating, or in fact, we want to traverse all the vertices without repeating any edges. Okay, so that's Euler tour. Then we have this Hamiltonian cycle. This Hamiltonian cycle means that it wants to ask us a question that is there a simple cycle, that is no vertices repeated. Okay, simple cycle means that there are no vertices repeated. Is there a simple cycle that connects all vertices in the graph? It means we need to touch all the vertices in the graph, but we do not want to repeat any vertex. Okay, we want to take certain edges that connect all the vertices in the graph, but it does not repeat any vertices. So these problems are NP complete, that their solution cannot be found in a reasonable amount of time. So for example, if we have a situation, a real world situation, and we prove that this situation is similar to this Hamiltonian cycle, then we can say that the solution is not possible in a reasonable amount of time, that or that the solution is NP complete. Similarly, there is this Knight's tour that's similar to this Hamiltonian cycle. And the last problem is the traveling salesman problem. And in this problem, what we do is that we want to find a cycle. That is, if this salesman has started from this specific location, it needs to visit all the shops in the area and then come back to the same location. And in this case, he should not also repeat the vertices. Okay, it should be a simple cycle. Okay. This problem again is a NP hard problem. So given an NP hard problem, if we prove that any problem that we have is an NP is similar to this traveling salesman problem, then we can say that it's an NP hard problem, and the solution to this should not be to find all the possible solutions and find the best one among them. Okay, so then there are some smaller problems that we actually would see the algorithms for. And the first algorithm is the minimum spanning tree. We'll see that this tree is used to maybe lay down an infrastructure of electricity in a new housing society, or maybe to lay down the computer network in a building, maybe to lay down the road network in a city, in a new city. So we essentially need we have a graph, and we need to find a minimum spanning tree from that specific graph. We'll see the applications. We'll see this specific algorithm in details in the next lecture. Then there are some shortest path algorithms on the graph as well. We would try to see the shortest path algorithms in this course. Particularly, we would actually have a lab session on implementation of an algorithm that is the shortest path algorithm. So that's it for today. We'll have a question answer session in the next class. And if you have any questions, you can ask.